Okay, so welcome at our third session of a reading group on the assumptions of physics. My voice is a little bit low because I'm not feeling very well, but we're gonna do it this anyway. So we are at chapter one. Let's see, we are at 1.3. And I need to repost the order of people. So, okay. Okay, so we are never gonna get this right. So there you go. Thank you, Artem. So why don't we and I need to share my screen so that everybody can see what we're reading. And there it is. Okay, so Artem, why don't you start?
Yeah, so last time we started point one. So you just I wasn't here last time, but I caught
Yeah,
up.
I would just go back to 1.3 because the math that we're
Yeah,
seeing the
sure.
last time, we have to have it fresh in our mind. So I would just restart.
Okay, so we have seen the importance of the connection between kinematics and dynamics. In this section, we'll explore this link more deeply and come to the following conclusion: the kinematics of a system is not enough to reconstruct its dynamics. And the example we have here is particle under linear drag. Um,
Yeah, start reading that as well.
yeah, well, let me do that. So let us first review exactly what the kinematics and dynamics are. Given a system, its kinematics is the description of its motion in space and time. Position, velocity, and acceleration are kinematic variables because they describe the motion. Kinematics is what Galileo studied and started to give a rigorous account of. The dynamics instead describes the cause of such motion. Force, mass, momentum, energy are dynamic quantities as they are used to describe why a body moves in a particular way. Dynamics is what Newton introduced, and his second law, expressed as force equals mass times acceleration, clearly shows the link.
Okay, Pranat?
Okay. The link between the two concepts seems important given the constitutive role of kinetic energy in Lagrangian mechanics.
Oh, that's kinematic
Moreover,
equivalence.
oh, sorry,
That's okay.
kinematic equivalence in Lagrangian mechanics. Moreover, while both Newtonian and Hamiltonian mechanics are dynamical theories, in the sense that quantities like force and momentum are intrinsic parts of the respective theories, Lagrangian mechanics seems to be a purely kinematic theory, as it is described only by the kinematic variables like position and velocity. Therefore, it seems useful to characterize the kinematics dynamics link as much as possible. Let's analyze a concrete example. Um, Suppose we
Rudra?
are given the follow. Okay,
Or
yeah.
Wiswich?
Suppose we're given the following equation, MA equals negative BV. The equation is in terms of kinematic variables and given initial conditions, X naught and V naught, it admits a unique solution, a unique trajectory. The solution plotted in figure 1.3 is X of t is X naught plus V naught M over B times 1 minus exponential of negative B over MT, and differentiate that, you get velocity. Differentiate that again, you get acceleration. Can we reconstruct the forces acting on this system?
Okay, we already went through it last time, but what happens here is that this acceleration is just a derivative of velocity in time. So you just have a linear equation. The solution of the linear equation is just the exponential, and the exponential has a minus sign here because there is a minus sign here. So now the position is just the integration of this function, and the acceleration is just the derivative of this function. And here you have the graph. The position goes up because it has an initial velocity, and at some point it stops. So the velocity has an initial, there is an initial velocity and it goes to zero because of the friction, and the acceleration also is another exponential and will decrease in time. So that's basically how it works. So next is ruling. Please look at the.
I'm not sure how to read the next part because it's 70% equations.
Yeah, read the text and then I'll describe the equation. We'll just pause and people can read it by themselves first.
The obvious answer seems to be that the constant m represents the mass of the system and F equals negative BV, the force. This is the case of a particle under linear drag. The system is subjected to a frictional force that is proportional and opposite to the velocity. If we set the Lagrangian as some multiple of the kinetic energy, I guess.
Yeah.
And apply the Euler-Lagrange equation 1.3, we have do a bunch of stuff and then get MA equals negative BV.
Right. So everybody look at that and try to see if you can make sense of it, and then I'll briefly go through it. Okay, so it shouldn't be that hard. You're just taking this Lagrangian and put it inside here. So you have that the derivative of Lagrangian with respect to the position is zero because there is no position as the Lagrangian. This Lagrangian is not a function of position. And so this part also has to be equal to zero. So first you do the derivative in the velocity, and the only velocity that appears here is outside the exponential. So everything else is a constant. So this 2 comes down, simplifies it just mv with times the exponential. And now you do a total derivative in time, meaning that you have to differentiate. Essentially, you're doing the chain rule. You're differentiating first by on the velocity, and so if you differentiate the velocity, you're gonna get an acceleration, and everything else is a constant. And then you're also differentiating in time, and so you're differentiating the exponential, and so this bm over t, this bm comes down. Then you can collect the exponential, and then you have the exponential ma plus bv, but this has to be equal to 0, and so you get ma minus bv. So it seems to work. Go ahead.
Okay. Therefore, we have a Lagrangian for the system. We can also find a Hamiltonian by just a bit substituting. Wait.
Yeah,
Okay.
again, I'll give like 20 seconds for people to look at the equation and try to figure out by themselves, because it helps if you try to figure out by yourself. Okay, so here we just have the definition of conjugate momentum from Lagrangian mechanics. So you take the Lagrangian, make a derivative in velocity, which you already did here. So it's basically this part. So this is momentum. And now you can invert the relationship between velocity and momentum. So the velocity is p over m multiplied by the exponential. To find the Hamiltonian, you just do PV minus L. And so we have V as a function of momentum. We substitute it here. And we have L, again, we want it as a function of momentum and not velocity. So we take that Lagrangian that had the V here, and we are substituting with the P. Right? We substitute V such that we have the P. right? So this is the V that we're substituting in the Lagrange. And then you just do the calculation. So you take the square of this. So now you're going to have the exponential here with the minus is going to have a 2, and you have 1 with a plus, so they simplify. And then you just have the P over M here, the P over M here, and it's 1 minus 1/2. And so you have 1/2 P square over M e to the minus. So note that in the Lagrangian we had the plus in the exponential, and in the Hamiltonian we have the minus. And then if you apply Hamilton's equation, you again take the derivative of the Hamiltonian with respect of momentum, and you get the expression, and the same thing with here. So what I want you to note already, there is something fishy, right? If you think that the Lagrangian is a kinetic momentum minus kinetic energy minus potential energy, and the Hamiltonian should be kinetic energy plus potential energy, you already have something that does not quite look right. Continue.
Yeah, so basically to obtain like the correct kinematics here, we have to kind of so our Lagrangian is greater by that exponential, and our Hamiltonian is
Smaller, yeah.
Is I think it's greater again because it should be like e to the minus 2 whatever if it would be kinetic energy, but it's so both are greater by the exponential than they should be.
Yeah. So that's exactly the point of all of this, and we are going to go thoroughly in detail with all of this, right? So that's why I wanted to review the math because we are going to see this in 3 different forms. So I think we are here.
The second equation tells us that momentum is constant P0. Substituting the constant in the first equation, we have the velocity as a function of time, which we can integrate. The kinematics, yep. And then you have conjugate velocity is a bit weird, or Q, that's the position, right?
Yeah.
Yeah. Position is accurate, it seems.
Yeah.
Yes. And the kinematics work perfectly, but the dynamics seem off because you have the conjugate momentum being exactly the same all the time.
Right.
First, as shown in figure 1.4.
So let's go and see that. This is exactly, the difference. So the position is still the same. This is the kinetic momentum, and this is the conjugate momentum. This is the energy, and this is the Hamiltonian. So this is the kinetic energy because there's nothing else. So this is the kinetic energy, and this is Hamiltonian. You see that the two things are off.
Okay. Yep. And first of all, based on the physics, one would expect the momentum to be decreasing in time, which we see is not the case. However, conjugate momentum is a constant of motion. For the energy, we'd expect the Hamiltonian to match the kinetic energy, which is mv squared, half mv squared. But if we express the Hamiltonian in terms of velocity, we have a negative multiple of, well, the time factor is square rooted.
Exactly.
That
So
is
the
energy.
difference, yeah. So the difference here is there is an e to the minus 2 here, and here instead there is the e to the minus 1. So that the factor for which the energy is dampened is different from the kinetic energy and the Hamiltonian.
That is, the energy decreases more slowly than it should. That is not good.
Okay, should I take it from here?
Yep.
Now, it is true that conjugate momentum is not the same as kinetic momentum, but the difference, as we will see much more clearly later, is caused by non-inertial, non-Cartesian coordinate systems and/or the presence of vector potential forces. We are not at all in that case. Also note that at time t equals 0, the momentum and the energy do match our expectation. but not after. Therefore, imagine a situation where friction is non-negligible only in a particular region. We would expect P equals mv to be valid before it enters, but not when it comes out. But wouldn't it come out in another region where we would expect P equals mv to work? This is strange. How should we proceed? There's a footnote for vector potential forces. The relationship is equation. This reduces to pi equals mvi if and only if we are in an inertial frame with Cartesian coordinates and no forces.
Okay, I'll just continue from here.
Yep. So I think we are a variable mass system.
Yes, so from figure, okay, wait, right, okay. So as it is typical in reverse physics, we will assume that things work in a reasonable way and that we simply have a wrong connection between maths and physics. Recall that we just started with an equation and we then interpreted m to be the mass of the system. Let's assume that m is a constant with units of mass and define the actual mass of the system as a ratio between the conjugate momentum and velocity. Looking back at figure at 1.20, it is shown as shown in figure 1.5. We have the following equations. This is the conjugate mass here.
This is we're defining the mass as the
Right.
ratio between the conjugate
As a ratio
momentum.
between the momentum as a function of time and velocity as a function of time, which is given as m into e to the power of b by m into t. And yeah, I'll just let you explain the formulas from here.
Yeah, you can start digesting it and then I'll.
Yeah, so I think it makes sense, the formulas.
So
Yeah.
basically, we're saying instead of saying that we know what the mass is, that the mass is m, we just we know what the conjugate momentum is, and we know what the velocity is. So we just say that the ratio between the two is the mass. And now the mass is a function of time. It's m e to the b minus t t b over mt. Then of course you can write now pt as the product of that mass and that velocity because we're just reversing things. And we can write the Hamiltonian now as essentially what we had before, and now we collect that the mass, this m e to the minus b over m, that coefficient comes down, and so now this is the mass. And now we have the correct relationship because we have 1/2 p squared over m equals 1/2 m v squared. So the fact that that exponential changed the sign here is just because we are putting the mass above or below the fraction, right? So things do make sense much more. So continue.
Now everything actually works perfectly. The relationship between velocity and conjugate momentum is respected. The Hamiltonian matches the kinetic energy. We just have a variable mass system. How and why does this work? Alina, you can continue.
Right, let us expand Newton's second law for variable mass system. Footnote 9. You could go down. Thank you. Note that in general, the variable mass system should take into account the momentum gained or lost by the system when the mass is acquired or ejected. In our case, we are assuming that no momentum is lost, which means that either the mass is acquired or ejected uniformly for all directions, or it is just an apparent change that depends on the change of coordinates. Okay. Right, we have, and then here's the equation. Well, yeah, this is just force equals time derivative of momentum. You expand that. Okay.
Okay, so we just got the definition, and now since the mass is a function of time, when we take the derivation of time, we have to use the product rule. So we have the ma on this side, but we also have derivative of the mass and time times the velocity. And then we can take the mass on the other side. And now we have that ma is equal to force minus this change in the kinetic momentum due to the mass.
Right. In particular, for our one-dimensional case, let us set f equals 0 and substitute m. Okay. So yeah, here you're substituting AI for the formula, f0, and the same for m. Yeah.
Yeah. So
yeah,
this becomes with the mass with the exponential. We're gonna take the derivative of the mass here of the mass here. So the b over m comes down on the exponential, and then again, like we had before on the Lagrangian, we have two exponential on each side. We can remove it, and we just get ma equals minus bv.
right. Therefore, the same equation, the same kinematics applies to a variable mass system that increases the mass over time. You can imagine, for example, a body that is absorbing mass from all directions so that the balance of forces on the body is 0. The body then is not slowing down because of friction, it is slowing down because momentum is conserved. And if the mass is increasing, the velocity must be decreasing at the same rate. The energy, on the other hand, will decrease because the square of the velocity will decrease faster than the mass increases. Okay, that makes sense. Shall I continue or?
Tobias.
Okay. In Newtonian mechanics, we can readily distinguish these two cases because we have to be explicit about forces and masses. In Hamiltonian mechanics, things are a bit more difficult because, as we will see later more precisely, conjugate momentum is not exactly kinetic momentum, and the Hamiltonian is not exactly energy. Yet, conjugate momentum and the Hamiltonian are not kinematic quantities. They are dynamic quantities, and therefore we can see that these would be different in different cases. In Lagrangian mechanics, this is even more difficult to see because it looks like a purely kinematic theory, while it is not. The Lagrangian itself is not a purely kinematic entity. As we saw, Lagrangian mechanics implicitly assumes kinematic equivalence, which is a condition on the dynamics as well. And the Lagrangian itself is used to reconstruct conjugate momentum and Hamiltonian. Moreover, if Lagrangian mechanics were a purely kinematic theory and told us nothing about forces, energy, or momentum, it would not be a complete formulation of classical mechanics.
So we have seen that the same kinematic equation can describe a constant mass dissipative system or a variable mass system. Is that it? Not quite. Recall that we mentioned that kinetic and conjugate momentum will differ in non-inertial frames. Note that we implicitly assumed that x and t represented the variables for an inertial observer, in the same way that we originally assumed that m was the mass of the system. Could the same equation then be describing yet another system, but in a non-inertial frame?
Okay, let's
No,
pause and see if there are questions on this section. So the thing that it's most important to me is that you can see very clearly that the equations are never enough to tell you what the physics is, right? That clearly we have the same equation that can be interpreted in a couple of ways, and you kind of need to understand what's going on. Otherwise, if you can just put math in and get results that are not really meaningful, right? So that's kind of the whole process here, is to figure out exactly when can we interpret this math in some physical way and when not.
So do I get like the argument correctly? So we start with basically was the Newtonian description of drag, and from that we get the equations of motion.
Yeah.
And then we just use, we find the Lagrangian that gives us the same equations of motion.
Yeah.
But then the argument is, if we look more closely, the Lagrangian is actually not for a system drag, but for a system that gains mass, right? Is that the argument?
Yeah, that we can. So the Lagrangian basically gave us momentum that and energy that didn't quite fit the interpretation of I have a particle under linear drag, but it fits the interpretation. I have an equation for a variable mass system that is slowing down because it's accumulating mass. And in fact, in the next section, we will see that there is yet another interpretation of the same Lagrangian and the same equation of motion.
By the way, this is like the question I had, but now it's partially answered. But in the first semester, like in mechanics, the lecturer drilled into my head that, and at that point, I kind of got the explanation that the reason is that we have variable mass systems, rocket equation, and such. So he drilled into my head that F equals ma is not completely right. The force is actually the change in momentum. And so is there a particular reason that here we start was F equals ma for the Newtonian formalism and not was this one?
I start so in the formalism when if you remember how we review it with saying that the force was the change in kinetic momentum.
Yeah, okay, that's true. Okay, great.
Right. So the fact that we are starting with an A equals minus B, BV, is because we are basically starting with that equation and see where we go.
Okay,
And so
I see. Thank you.
when we do discuss the variable mass system, we have the better equation with the change in momentum, right? So we go back to that. And again, this is not the rocket type thing because with the rocket, you are actually, spitting mass somewhere else. So the whole system is losing mass, like it is losing momentum, right? So you need to take that into account. And so what we're saying here is that the mass is changing, but we still have something that is conserving the momentum. And so if you would imagine that a rocket is firing off the mass in all directions such that it's completely perfectly balanced, then the momentum wouldn't change. And this, you would have that equation because there is no momentum change. So this is sort of a way to say, okay, let's reinterpret the same equation, and let's say that there is a change in the velocity, but the momentum is there is no change, and the only thing that is actually changing is that you're accumulating mass in this case. So yeah,
Okay.
we are trying to do all these things, sort of precisely because otherwise we will get it wrong again.
Okay, can I try to understand like more general, like what the difference between the two systems is? Because if you would be only able to observe the trajectory of whatever object you have, the two match, right? If you have something that accretes mass or you have something that is just under drag in the specific, like a constant drag that just depends on velocity everywhere. You would not be able to distinguish the physical systems if this is the only thing you can observe. But then like I assume like I can put the same system under like slightly different circumstances, like make the drag only appear in a specific region. I would like in that region get the same trajectory, but not outside. So
that, or you could just measure the mass, right? If you were able to measure the mass, then you would see that in one case the mass is not changing, and in the second case the mass is changing.
yeah, and I guess yeah. So it's the fact that I can put the same system in different contexts, and I assume like my modeling should work like more generally, where I can see the differences. Does that make sense?
So you could like that's one way, but in this particular case, you just need to be able to measure the mass. So if you were able to not just measure the position in time, but also the mass for however in however way you see that it's the same material, but it's getting bigger, right? Then you have a sense that it's that the mass is increasing. Then that would be enough to be able to distinguish the two systems.
Okay, but at the end of the day, if I want to measure the mass, I will put the same system in different circumstances, like
Yes.
an experiment, and then probably watch the trajectory anyway, or
Yeah.
I guess you would balance the forces or something. Whatever, yeah. Okay.
Right. So like if to measure the mass, you have to sort of act on the system differently, then yes, you are in the same condition. But if you're able to measure the mass in a way that that just you're not affecting the trajectory, then you might be able to do that. Okay.
Okay, so this is all kind of connected into how we find out what specific shape forces have. Like, how do we find out that gravity needs like 1/r potential or 1/r squared force,
Right.
and all of that. So it is kind of modeling.
Right, and you need to be able to, as sort of going back to what you're saying, to be able to control all these parameters, right? So if you were not able to control the mass of the system, then you're not going to be able to understand what the forces are because you can't.
Yeah.
So the important thing here is that the kinematics itself, just looking at the trajectory, is never enough. Okay? Who's next?
That's me. Okay. Non-inertial motion. Let's compare the motion of a particle traveling at constant velocity in an inertial frame using t as the time variable, and the motion of a particle decelerating exponentially using t hat as the time variable. So x of t would be x naught plus v naught t, and x of t hat would be x naught plus v naught times m over b times 1 minus exponential of minus b over t times t hat. Note the striking similarity. We can simply set t equals m over b times 1 minus exponential of minus b over m times t hat, which clearly takes us to a non-inertial frame, since uniform motion is no longer uniform in the new frame. Should I pause for that?
Next one.
Okay. Let's study how Newton's second law changes if we make a change of time variable while keeping the position variables unchanged. So if we leave t hat as t hat of t, but the force we write the definition, which is differential with respect to time of momentum, and we write the velocity as differential with respect to time of the position. We get the following. Can I continue? Or should I pause?
So here we're just using the chain rule. I think it's obvious, but go ahead.
Yeah. So if we set m hat as mass times differential of t hat with respect to t, we can express the previous equation in the following form. So we utilize the final expression from 1.31 and 1.32 to write it in terms of m hat, and then we finally arrive at differential of t hat with respect to t times f hat.
Right. So what we're basically doing here is that we have the position is the same, but we're deriving with the t hat. So this is now the velocity in the new coordinate, but this now is the derivative of the time in the new coordinate with the kinetic momentum of the new ordinate. That's the force seen by the other guy. And so we have this, that the force changes with the change of time. Finish up the paragraph?
Oh, okay. This tells us that the second observer will see an effective mass rescaled exactly by the ratio between the time variables. Note that this is exactly what happens in special relativity. The clock for a boosted observer is dilated by a factor of gamma, which is exactly the factor used in the relativistic mass. If T is the time variable for an inertial frame, and T of T hat is a nonlinear function. The resulting frame will be non-inertial, and the observer will see an effective variable mass system. And we have a footnote for
Yep.
the relativistic mass, which says it may be surprising to see a photorelativistic effect showing up given that no assumption on spacetime has been made. As we will see, these types of connections between different theories come up often in reverse physics.
Okay.
Okay, but ironically, in
Um,
special relativity, you would switch between inertial frames, and it will still be that will
Correct.
still
Yes.
show up, right? Okay.
But the point is that even when you're switching between inertial frames, there is a clock difference. Like your proper time is different from my proper time.
Yes. Wait. So if we switch between inertial frames, gamma would be constant, right? But here it changes over time.
Yes. Yeah. In that case,
And
in the case would be a constant. Yes.
Okay.
Yeah.
If we look at our problem this way, the rescaling of the mass then is not due to a truly variable mass, but a variable effective mass due to the slowing down of the clock. The body slows down because the non-inertial time is slowing down, and the body appears to stop because the clock becomes infinitely slow. While this might sound like a contrived case, these are exactly the type of situation the fully relativistic theory, i.e. one that works for all definition of time and space variables, needs to take into account. On the surface, it sounds similar to what happens in general relativity with a black hole. An observer that sees someone falling into a black hole will see him gradually slowing down as he approaches the event typo there. That's the even horizon.
Oh, look at that. Okay, I'll go fix it.
Event horizon and asymptotically stopped there. The observer falling into the black hole instead will perceive his time flowing uniformly, and nothing special will happen as the even horizon again is crossed.
Nobody's ever noticed that. That's funny.
We should figure out what's the odd horizon then. Maybe it's the one in white holes. Okay.
Say it again?
Anyways.
Yeah. Okay, I'll make a note and fix it later. I don't have the document open. Okay. Okay. So next.
Did we skip Rudra?
I believe so.
Okay, maybe you go and then I'll go after.
Okay. Okay, we can verify that this gives us the correct effective mass, which is equation 1.34.
Okay, this is horrible to read. Yes. So again, this is just applying the Fourier transformation that was defined. Did I write the T? Oh, there you go. This is the expression here. And so we are just now taking the derivative of time with respect of the other time. So we're just taking this expression and derive it in time. The constant comes out, the one goes away, and here we're just taking the b over m down, which is going to simplify. And again, we get the same magic factor of the e minus b over mt. And now the rescaled mass, we saw that was the mass in the inertial system times the change, so t hat over t. But since this is a total derivative, this is just the inverse of dt over dt hat. And so it's this with a plus sign, and so we find that the mass is the mass in the inertial system times the exponential.
And we can verify that we get the same equation by plugging in the time transformation in Newton's second law with the zero force. which is 1.35.
Yeah, I'll give you like 10 seconds to look over it. So basically the key is here. We are basically substituting the time derivatives so that we get the mass rescaled and the other factors above. And again, we have this derivative of m, the exponential v. So now the m is the constant. Here we derive with the exponential, so we get the b over m factor. And then we derive the v hat, we get the a hat. We collect the exponential, and again, we have bv plus ma. And so we get again the same equation. So it's very funny to me how like all these terms are sort of playing these roles and they always appear sort of in slightly different ways, but at the end of the day, you get always the same result.
Okay, so these are all hats now because in the no hat, the original frame, it's just standing still, right? There's no
Yes,
force on
in the
it.
original frame, you're just going with a linear motion, with a uniform motion, because there are absolutely no forces, right? And
Okay,
now
so
we are in the inertial, non-inertial frame, and so that's where you see all these apparent forces, which again are not caused by the change in a spatial variable, are just caused by the clock. The clock is slowing down.
Note that the expressions for momentum and energy will match the previous case because the system in the non-inertial frame looks like a variable mass system.
Okay, the relationship between kinematics and dynamics. This last case highlights a more subtle issue. In the two previous cases, we were in the same inertial frame. We saw the same trajectory, the same kinematics, but we couldn't tell whether we were looking at a fixed mass system under linear drag or a variable mass system. We couldn't tell the dynamics. Now we have the same system, a constant mass particle under no forces, described in two different frames, one inertial and one not. The motion of the system will naturally have different representations in the different frames, but this does not mean but this does not mean the motion or the causes of motion are different. It's the same object. Therefore, we have the same motion even though we have different expressions for the trajectory. The expression x of t, then, is not enough to define kinematics if we do not know exactly what x and t represent physically, if the frame is not given.
While typically one proceeds by defining the frame first and then the dynamics, that is, the forces acting on the system, here we have followed a different approach. We first defined the dynamics, that is a constant mass system under no forces, and then we found the frame that matched the given kinematics, that is a trajectory or the relationship between the velocity and acceleration. Given that Lagrangian and Hamiltonian mechanics are frame invariant, an intrinsic characterization of the system itself is exactly what we should be looking for. Saying, for example, that a system is subjected to no forces or to a linear drag is not frame invariant because forces are
Did we lose him?
no.
thanks.
Finish my paragraph, so Alina can continue if she's still here.
Right.
Yes.
It is clear the type of apparent variable mass due to non-inertial frames is unavoidable. We want to have a consistent theory with invariant laws. Therefore, both Lagrangian and Hamiltonian mechanics must include these cases. However, it is not exactly clear what to do for true variable mass systems. From a cursory look, it would seem that everything is fine and there is no harm in including them. Yet again, from a cursory look, we seem to have a Lagrangian for a particle under linear drag. As we will see later, there are implicit connections between Lagrangian and Hamiltonian mechanics on one side and thermodynamic statistical mechanics and special relativity on the other. Given that it is not clear to us whether these connections hold or not, Footnote 12, for example, areas of phase space are connected to entropy. Does this connection hold with a variable mass system? We will concentrate on the constant mass case from now on.
Was it me? Next?
Yeah.
Okay, thanks. Let's recap what we learned. The biggest point is that we can't simply look at the kinematics and understand the causes of motion. The different formulations have different ways to relate the dynamics and the kinematics. Newtonian mechanics is the most clear about the dynamics as it makes us clearly spell out what is going on. This, however, comes at a cost. The equations are not covariant, meaning they have a different expression in different frames. The second law, in fact, is valid only for inertial frames with Cartesian coordinates. It is only in these frames, in fact, that a body will proceed in uniform motion if no forces are applied to it. If we are in polar coordinates, for example, the trajectory expressed in radius r and angle theta will not be linear, even if the notional force is, if one looks closely, a bit ambiguous. In principle, we want to write both the second law, F equals ma, and the expression for work, dw equals f dx. If dw is invariant under change of position variables, the force should be a covector, and therefore dw is f lowercase I dx uppercase I. But since the acceleration a will change like a vector, we also have f as a vector is equal to ma, another vector. The notion of force in the second law and in the infinitesimal work are slightly different, and they coincide only if we are in an inertial frame in Cartesian coordinates. Let's see.
On the other side, Hamiltonian and Lagrangian mechanics are coordinate independent. The laws remain the same if we change position variables. This makes them more useful in many contexts. Lagrangian mechanics is more useful when trying to study the symmetries of the system. Hamiltonian mechanics is more useful for statistical mechanics and to better separate degrees of freedom. However, this comes at a price. Hamiltonian and Lagrangian mechanics apply in fewer cases than Newtonian mechanics. As we saw, linear drag may look like it has a valid Hamiltonian or Lagrangian, but it doesn't. For quadratic drag or friction due to normal force, one cannot find a suitable trick and is forced to use Rayleigh's dissipation functions, which modify the Euler-Lagrange equations. This is not a coincidence. While Newtonian mechanics links kinematics to and dynamics by choosing a particular frame, Hamiltonian and Lagrangian mechanics do so by fixing a type of system. It is the implicit knowledge of the type of system that allows us to reconstruct the dynamics just by looking at the kinematics in an unknown frame. What we need to understand then is what exactly is this restriction.
So, isn't there like one of the issues basically here is that you don't really have conservation of energy in the original system, right? That makes the Hamiltonian behave weird.
Right. So you have conservation of energy when you have a system that it's essentially isolated, right?
Yep.
And now if you introduce apparent forces, now your system is no longer isolated. So it makes sense that when you go from an inertial system with no external forces to what's it called? A non-inertial system where there are apparent forces, then you're going to have the balance of energy is going to not work out in the same way.
So could you like, in this example of like linear drag, could you make like a fake like other object that like takes all the energy from the
I think for that you would have to have an external force on the yeah, okay, so you're basically saying I have an inertial system and I have I do not have and I have an external force, and then I want to find a non-inertial system that has an apparent force that cancels out that real force. You should be able to do it.
Yeah. Okay.
And let's see, is anything that we have done here can be...
Mhm. Okay.
So yeah, we should be able to take, let's see, let's say that we had, and let me think about it. There has to be a way, right? Because if we imposed, let's say that we had this clock example, right? We're changing the clock, and we saw that if we slow down the clock and things appear to slow down. Now imagine that I am accelerating the objects with the same exact acceleration, such that when I slow down the clock, now the system does not seem to slow down anymore. It seems to be going uniformly in time. So you should be able to do it.
Anyway, we now turn our attention to Hamiltonian
I
mechanics.
don't think we should start the new section, because otherwise it's gonna be like last time that we started and then we have to
Okay.
repeat it anytime. So I would just don't think there are any question on the chat, because I don't see many many viewers this time. I don't know if there are any other general questions on this or the whole thing. We just leave it to that. Otherwise, we can just close early. I think it's better.
Yeah, I was just scrolling ahead and like I just noticed how omega A of B in the next section just looks like the matrix representation of complex numbers, or like just of I. Right there, at
Where is
under
it? Oh, there you go.
mathematical factorization. Yeah, yeah. So I was wondering if there's like a, I don't know, any other reason why I just pops up over here?
I think oh, sorry. I think if you look ahead, it might be related to the fact that basically I don't know, I haven't read it, but I'm just seeing the picture later, and I think we might have the case that in phase space you have this basically rotating vector field. So that's
So
probably
similar
why.
to
I'm not sure.
similar to how we go from Cartesian to polar coordinates, that kind of deal. Is that what you mean?
I think I didn't understand the question. So there is omega here.
Yeah, I'm just curious as to why the like I pops up. Like this is basically the representation of I, right? Minus I specifically. I was just interested in that.
No, this is just a matrix. So it's 0, 1, -1, 0. I don't see the I. What do you mean by I?
Complex
Because
numbers
symplectic.
The,
Sorry,
yeah,
I was just saying that symplectic transformation, this omega is actually the standard symplectic form.
Yeah.
So for orthogonals, you would have O transpose O equals identity. For symplectic, you would have a J, and that omega is that J, where J squares to -1. And you can map
I see.
Okay.
you can map like the real transformations to complex ones by using the J as an almost complex structure, which is generalized in Kähler and Calabi-Yau manifolds later.
I see. I see. Could you? Okay, I'll just text you in the server then.
Yeah, no problem.
Okay, cool.
Yeah. So that there is a relationship between sort of this idea of almost complex structures and symplectic, because you can do these things, and the physical significance, it's something that I'm trying to, let's say, put together so that I have the same type of argument that I can use in both classical and quantum mechanics, but I'm not there yet. So because I don't have the single space on which I can say the same things, essentially. That's my problem. Any other questions or comments? Then I think we stop it here. Thank you everybody for joining, and thank you for anybody who is watching this later. And we'll see you next week. Bye.
Bye.
And the stream.